Welcome. Thanks for joining today. This talk is going to be about using reinforcement learning techniques for recommender systems. Before we get started, let me introduce myself. My name is Claire Longo. I'm an engineering manager currently working for Opendoor. At Opendoor, we're doing some really exciting stuff with machine learning. We buy and sell homes, and we're using the machine learning to predict the value of the homes and how the homes appreciate over time. And my team is focused on developing and maintaining platform tooling to support these machine learning models. So we're an MLOps platform team, and we're working on maintaining and deploying these models into production. Prior to Opendoor, I've worked for Twilio, where I was also leading a full stack machine learning team. And then prior to that, I also worked as a data scientist and also as a machine learning engineer. So I've been on the research side as well as the engineering side of things. And I worked for a while for Trunk Club, which is an e-commerce company. And that's where I really developed this love for recommender systems. We'll talk a little bit more about that today. And currently, one of my interests is reinforcement learning. And I've been studying how people are using reinforcement learning for recommender systems and became very inspired by it. That's kind of what led to this talk today. And that's what we'll be covering in more depth. As I go through the talk, you can submit questions in the QA panel you see on your screen. We'll be monitoring them and answering them in our Slack community. So you can also join our Slack community and ask questions there as well. Cool. So what are we going to talk about today? This talk is really geared towards people who maybe already have a good understanding of machine learning, recommender systems. I will give an overview of these. I'll talk about recommender systems and reinforcement learning at a high level, but we won't spend a lot of time there, and I'm not going to go into deep mathematical depth. Instead, this talk is really meant to present some things that could be a good jumping off point if you want to take this stuff further, and maybe as a source of inspiration of how you might use these algorithms for your applications. So we're going to do a quick overview of recommender systems, reinforcement learning, and then we're going to talk about how to take these traditional recommender systems that are in the machine learning framework and kind of reframe them as reinforcement learning algorithms. And then we'll talk about some challenges that traditional recommender systems have. This is the cold start problem, echo chamber effects, long tail effect. Some of these might sound familiar. But the reason I want to chat through them today is that the reinforcement learning can actually offer some ways to mitigate these challenges and to even solve for them. So I'm going to present those and show how the reinforcement learning can help. And then last but not least, metrics and monitoring. We're going to talk about how to maintain your recommender systems over time and some really cool metrics that you can use to do this. So let's jump in. What is a recommender system? It's basically a personalization algorithm that's used to drive things like item recommendations. It can be reinforcement learning, deep learning, machine learning. There's a lot of different forms that it takes, but its goal is usually the same. It's typically recommending items to users. These are some of the more interesting algorithms because we encounter them every day, all the time on different platforms. They're used within e-commerce. You'll see them on newsfeed personalization. You see them in music recommendations, movie recommendations. It's also common as a click-through rate optimization algorithm, CTR, and many, many more. So these are algorithms that are really impacting our lives day to day and are pretty well studied. So before I jump into the reinforcement learning side of things, I want to talk about the more traditional recommender systems using machine learning, and we'll use that as a base. So these more traditional algorithms, as many of you are probably already aware, they rely on user data and item data. I pulled a simple example from Amazon, just as something that I encountered in my day-to-day, just to help us frame what these algorithms normally look like. And I'd like to think of these algorithms in three different categories. There's content-based filtering, collaborative filtering, and hybrid systems. So the content-based filtering uses that item data that I talked about, and that's the plot you see the recommendations on the lower right on the slides. It just looks at the attributes of that item, the price, the color. There's a lot of attribute data available to us, but I'll look at those and just calculate similar items to put in front of the user. The next one is collaborative filtering. So this relies on detecting groups of users that are similar and making recommendations within those groups. So it's really relying on that user data. It'll use past user interactions such as ratings, clicks, purchases, reviews, and it's looking at the historical purchase patterns over time and automatically identifying groups of similar users. And then the recommendations are made by finding items within those groups that specific users have not interacted with yet. So it's kind of when you see that people who purchase this have also purchased these other recommendations, that's usually what's driving those. And then last but not least is the hybrid recommender systems. These are my favorite kind of recommender systems. They are called hybrid because they use both the user data and the item data. When we talked about content and collaborative, those use only one of them. One uses item data, one uses user data. But machine learning really benefits from a lot of data. And so when we can use all the data available to us, that's where we can get the most power out of our systems. So there's a couple algorithms that you can use for this. I personally like factorization machines. It's a linear model, so there are some limitations with it, but it's a good place to start. And then there's a lot of deep learning recommender systems that use both sources of data here and offer really elegant solutions. So what is the difference between machine learning and reinforcement learning? Machine learning needs a lot of historical data to learn. It learns patterns by looking at a large amount of historical data, encoding those patterns mathematically, and then using the patterns it learned to make predictions and forecasts for the future. Reinforcement learning, alternatively, is a live learning algorithm. It learns from trial and error. It doesn't need any historical data to learn, although that can be helpful in some situations. Instead, it relies on introducing new patterns into an environment and learning from the response of those patterns, learning from how the environment responds. So let's dive into reinforcement learning a little bit more. This is how I like to think about it. It's really a set of live learning algorithms that work within an environment. And in that environment, there are agents. You can think of them as robots or algorithms. And these agents take different actions, and their goal is to optimize some kind of long-term or short-term outcome. So the way I like to think about it is have the agent here, which is the brain or the robot. It is living within some kind of environment. This environment is defined by your data and the possible set of actions. The agent will take some action in this environment, and then there'll be some kind of response. And based on that response, the robot will learn and then take a different action. And every time I take an action, the state of that environment and the agent's observation of that environment changes. But the benefit here is we can try a lot of different actions and see what that reward is, and then through trial and error, we start to learn this optimal set of actions that the agent can take. So I do like to kind of frame this mathematically. This is the depth of math that we'll get into in this talk. I won't go any deeper than this, but I do think that this is a really helpful way to frame this as we think about it. So for reinforcement learning, you have the state of the environment at a certain time step t. You have a reward, and that's the result of the action that was taken at that time. And you also have the action itself. And a set of actions can make up a policy. And our goal here is to really find that optimal policy, which is denoted as pi, the function of pi. What reinforcement really seeks to do, and just representing it mathematically here, is it tries to create this policy, define this optimal policy based on the rewards that it's seen from different actions that were taken. So through trial and error, it will start to converge to this optimal policy. And we're really just trying to mathematically optimize this value function here that I've represented. So reinforcement learning has something really cool and somewhat unique that is called the explore, exploit trade-off. This is how the agent is able to learn by trial and error. As this algorithm in live real time seeks to determine and follow this optimal policy, this correct set of actions, it can also continue to explore alternative actions. So you know what the right action would be at a certain point, but you also wonder if maybe there's a new alternative action that maybe didn't exist or you just haven't even tried yet that could actually be better. And this is tunable, but you can always set thresholds here to continue to explore by introducing new randomness and trying different actions as opposed to following that optimal policy that you've found. And this allows these algorithms to really adapt in almost real time. It's very useful if you're in a situation where you expect the environment to change and you want to be able to catch that automatically. For example, the housing market might change after we've deployed a machine learning algorithm. And through this kind of explore, exploit trade-off, we'd be able to identify that and adapt the algorithm more automatically. Whereas with traditional machine learning, if your environment changes from underneath you, you might see that effect in your model. You'll see like model drift, and you might have to go back to the drawing board, seek more data, try a different modeling approach, see what kind of model you can train that will work better in this new environment. Whereas with reinforcement learning, it will try to automatically detect and update the policy based on changes. So let's frame a recommender system as a reinforcement learning problem. In this context, the agent is going to just be your decision-making mechanism. This is the thing that is making product recommendations. The action is just the product recommendation itself. And then the reward is the user's response to that item recommendation. So the agent takes an action by recommending a certain thing, and then the user is going to generate that reward by either clicking, not clicking, purchasing, thumbs up, thumbs down, rating, any kind of interaction that user has with the item, whether positive or negative, is great feedback loop data, and that's what we consider the reward in this situation. And then the environment that we're trying to define mathematically is really just defined by your user and item data and possible actions that might be taken. The environment can take on different states based on historically what has happened up until now, and it can also be partially observed. The agent may not be able to see the entire environment, but it can observe parts of it, makes decisions based on that. So if we're going to go further down the path of using reinforcement learning as a recommender system, there are quite a lot of algorithms to choose from. The first one I would start with is contextual multi-arm bandits. Multi-arm bandits is a very simple reinforcement learning algorithm, and the contextual multi-arm bandits leverage both the user and item data. So it kind of allows us to have a hybrid recommender system that's going to use all the data available to us to make the most personalized recommendations possible. But it's also still it's reinforcement learning, so it has that live explore exploit kind of trade-off. It's a really simple algorithm, but I like to start there. I like to think of it as like multi-arm bandits are to reinforcement learning as linear regression is to machine learning. It's a very simple algorithm. It's a great place to start, and it works surprisingly well for many complex problems. And when I start there, it's often where I end up just stopping because it works so well. If you want to go beyond that, there's both value-based methods and policy-based methods. So the value-based are really looking at determining what the reward for certain actions are. So it's doing a lot of exploration and trying to estimate what this reward is for each action and building a policy based off of that. And then the policy-based method doesn't really look at the specific value of each action, but instead it's going to look at your overall policy and allow you to optimize that mathematical function. And these fit really well into like a deep reinforcement learning framework and can be really fun to work with. And then beyond that, there's model-based methods. So we talked about that environment. It's really defined by just the world that this agent is living and taking actions in. And the environment is sometimes impossible for us to know and code up. And even if it is possible to code it up, and we know all the parameters that make that environment, it could become very tedious to code it up. So for that reason, we can just model it with machine learning. So even though we're doing reinforcement learning techniques, if we do a model-based method, we can still use machine learning to create a probabilistic model of the environment. So moving into challenges and gotchas, potential pitfalls of recommender systems and how using reinforcement learning can offer some alternatives. So the first problem is the cold start problem. This exists in almost every recommender system use case. This happens when our users are new to the system or new to us, and we just don't have much data on them to make a personalized recommendation. In that case, when the user comes to us, we using our machine learning or reinforcement learning algorithms, we really can't get that level of personalization that maybe the user expected or wanted when they came to our platform. So we can use reinforcement learning to kind of jumpstart this user experience and make it personalized right off the bat, which is pretty cool. Using a very simple reinforcement learning algorithm like multi-arm bandits, we could put something in front of these users that start randomly showing a couple items, and then based on how that user interacts with the items, these we can start to adapt almost in real time to those user preferences. There's two benefits of this. It does get items in front of our user right away. It drives towards interactions like a click or a purchase, and that data can be collected as feedback and used to put into like a more long-term algorithm, like maybe machine learning or a different RL algorithm. But it also provides like immediately kind of that algorithm assisted personalization that maybe we might benefit from. And then next is the echo chamber effect. This is a really fun one because it is a result of using algorithms as personalization techniques, but its impact is kind of beyond ML. Like there is psychology sides of this, there is policy sides of this, ethics. It's a really interesting problem, but I'm not going to get too much into that. I'm just going to talk about the mathematics and the reinforcement learning around it. But basically what this is when you're using kind of those user-based algorithms that find users similar to yourself, group you in a cohort with them and starts making recommendations based on how those users are behaving. The impact of that is that although it can kind of optimize some metrics, we're looking to optimize like clicks or opens or engagement, it can also start to make the user's world a little bit smaller instead of bigger. And I believe that personalization should really make our world bigger. It should be introducing us to new things that maybe we never would have discovered on our own or from our peers that we actually find out we love. And that's not always what you get with these kinds of algorithms. Basically what happens is like, the reason it's called the echo chamber effect is your own kind of thoughts and preferences are just echoed back at you from the algorithm. Like the algorithm has learned so well what you and people like you enjoy that it's just converged to that. It's just going to show you things that we already know that you would really enjoy instead of taking a risk and putting something a little bit outside the box in front of you. So for this reason, I do really like reinforcement learning as a recommender system because it's always going to have the explore exploit trade-off that I talked about. The reinforcement learning is always going to put totally new, weird, different items in front of this user just to see how they'll interact. And if the user does like that item, it can start to learn new patterns and learn more about this user than we did before. So this reinforcement learning solution kind of allows us to introduce some randomness into our system so that we don't end up in this echo chamber. And I don't think it's a full solution to this, but it does provide kind of a mathematical framework that gives users new opportunities that the more traditional algorithms would not. And then the last challenge I want to talk about is the long tail effect. This one is one that I got to see up close and personal. When I was working in e-commerce, I trained an algorithm that had this challenge, and I got to dig in and try to understand what was going on here. So basically what this is when you think about a catalog of items you have to recommend, there's going to be popular items in that catalog and maybe not so popular items. And machine learning models need a lot of data to learn effective patterns from. And where we have a lot of data is those really, really popular items. So it's common that these traditional machine learning recommender systems will start just defaulting to recommending very popular items because that's where it's learned to recommend optimally. This can be fine, especially if you have a lot of popular items in your space, but I worry about it in the context of e-commerce or in the context anywhere where you just have a small set of products to work with or context of movie recommendations. Because in that context, I would argue that the user probably did not need an algorithm to discover these very popular items. They're already well known, they're already talked about. And the case that I saw in e-commerce is our algorithm was defaulting to very, very commonly recommending a white t-shirt. And in this context, users were coming to us for a personalized experience. It was a personal styling service. They wanted outfits, they wanted items that really matched their lifestyle and their personal style. And my concern is that most people kind of already own a white t-shirt, and it probably didn't feel that personalized to get this as a result of a personalized algorithm. So when I dug into this, I realized it was what is called the long tail effect, and that's the plot on the lower right. All the popular items are what we call the head of this plot, and then the tail are the less popular items. And by popular, I just mean they have less user interactions. So out in the tail of this plot, you have new items in your inventory that no one's interacted with. Those are not going to get recommended. You have really unique items that could really match someone's very unique interest or personal style, and that getting a recommendation of those items could feel extremely personalized. But if the algorithm can't learn from this data in here, then it's not going to be able to make those recommendations. So again, I don't think it's a full solution, but I do feel like it's helpful. I would rely on the explore exploit framework of reinforcement learning here. It allows us to introduce new items in front of the user and see how they respond to it. And if they respond well, then the algorithm will adapt and learn to personalize even better for that user. So if we introduced a framework like this, I think we could have overcome what I would call the white t-shirt problem of recommending basic things. The interesting thing about this challenge, and the reason that I became inspired to look more into recommender system metrics, is when we looked at my algorithm that was doing this, its metrics looked great. People were keeping this t-shirt, and so our revenue was fine. But when you looked at like how many users who kept the t-shirt actually returned, it was not what we wanted it to be. So although people were keeping this t-shirt, it was a good buy, it's basic, it was a good price. It wasn't really offering the personalized experience that we wanted it to, but in our like traditional recommender system metrics, we didn't see that at all. So because this is Arize Observe and I love metrics, we're going to talk about metrics and monitoring for reinforcement learning. These are relevant both for like machine learning and reinforcement learning. So in general, just recommender system metrics. So let's say you got a reinforcement or a recommender system model into production, it's working, it's live, it's making personalized recommendations to our users. How do we evaluate and monitor it? Or even before we're in that phase and we train the model and we want to know if it's good enough to put in front of our users, what should we be looking at? So there's 3 metrics I'm going to cover here. I think each one has its pros and cons, and none of them should be used alone, as we'll see. They work well together. So first up is map at K and mar at K. These are just your traditional precision and recall metrics. They are adapted to work for recommender systems. So recommender systems are really just ranking algorithms. They're returning a ranked list, maybe a list of 10 items ranked by most relevant to least relevant. This is just a calculation of precision and recall for that kind of prediction. And it's adapted to evaluate how well you're ranking. So are your most relevant items really at the top, or does the relevancy go down as you get further down the list? So they're both great. Map at K is kind of parallel to precision. Mar at K is parallel to recall. K is adaptable. You can do a list of 10 items, 5 items too. These are always like where I start, especially map at K. I always use that to evaluate my ranking algorithms, but it should be kind of done carefully because I don't think they tell the whole story. For example, like your map at K can look fantastic, even if your model is suffering from kind of that popularity bias we talked about as an effect of the kind of long tail trend. So the next metric that I love to look at is coverage. This one's really simple. It's just the number of items that your algorithm is able to recommend. So for example, if you have 1,000 items in your catalog and you can recommend 500 of them well, then your coverage would be 50%. You're able to kind of recall and recommend 50% of what's actually in your inventory. This one is like, be cautious with it because your coverage will be 100% if you have a recommender system that's spitting out totally random stuff. And that's obviously not the personalized experience that we're trying to give to our users. So I find this metric really useful in conjunction with map at K and mar at K. And I also find it really useful for live monitoring. So what I like to do here is I use it to compare models. If I got 3 or 4 models I want to choose from, I'll look at some other metrics along with coverage to help me choose what I feel like might be the best for that use case. And then I get a good sense of what coverage is for that algorithm, put it into production and start monitoring it. And if you see a huge significant change in your coverage, it can be a very interesting flag that's telling you to go dig into something. For example, if you are doing like clothing recommendations and suddenly your coverage drops because we entered the spring season and we have a ton of new inventory that the model hasn't really been able to pick up or learn to recommend yet, you'll see this huge decrease in coverage. And without monitoring something like this, you might not really realize that trend happens. And even like more complex trends than that. But it's really just a great way to flag that, hey, something has changed here in how this algorithm is working and the predictions that it's probably putting in front of our users, and indicate that we should go look at that some more. And then last metric I like to look at is personalization. This is just a dissimilarity between the user's list of recommendations. So it's just looking at a list of 2 users' recommendations and calculating how different they are. It's a cosine similarity metric. This one is really useful actually as a unit test in your CI/CD pipeline, because you can make 2 test users that have like very distinct preferences. There's no intersection in their Venn diagram of their preferences. Like maybe one person loves action movies, one loves romance. And theoretically, like your recommendations to these very different users should be very dissimilar, should be very different. And so you can frame like a small unit test around this with some fake users. I love to put that in the CI/CD pipeline to kind of validate the model as you're changing it and pushing it to production. It's also like you can try to calculate this across every user pair, but it's going to become like pretty computationally intensive. I think a better way to look at it might be placing your users into similar cohorts and then looking at the personalization between those 2 cohorts. So if you have 2 very different groups of users with different patterns, the recommendations they're getting should be dissimilar, and that's a good metric to keep an eye on. That is all I had. Thank you everyone for joining. I do want to talk through some references that helped me learn about this in case anyone is interested in doing a deeper dive. First up is Mastering Reinforcement Learning with Python. This is a really hands-on book. It'll make you code contextual multi-arm bandits by hand, which for me is the best way to learn, is to just code it up. So this is a great reference for a deep dive. I also wanted to link the ethical algorithm because this does talk a lot about the explore-exploit trade-off of reinforcement learning that we talked a lot about today. And it's kind of taking this in a different direction. It explores how we can adapt our existing like machine learning and other algorithms to account for biased data and start to introduce like new patterns to kind of undo the bias that are in our systems. So it's a really cool take on ethical AI. I've read a lot of ethical AI books, and this is the one that actually offered like a mathematical solution that was very actionable. So I was really excited to see that, and it's a fun read. And then on the third item here, DeepMind has some great references on reinforcement learning, and it's free, really good resource there if you want to learn more. And then last of all, some shameless self-promotion. I did create a Python library for recommender metrics. If you want to use map@k, personalization, coverage, some of the metrics we talked about here, and there's some other ones in there, you can check it out there. It is not as well maintained as I would like it to be. I hope to do a new release next month. But if you want to contribute, catch some bugs and report them so I can fix them, that's also helpful. And if you have any additional questions, definitely join our community on Slack, reach out, we'll be answering more questions there.